This presentation, Introduction to Air Sensors, was developed by the U.S. Environmental Protection Agency, Office of Research and Development. It provides information on air sensors for audiences with varying levels of experience, which includes both new sensor users and more experienced users. This presentation will cover background information on air sensors, differences between air sensors and regulatory monitors, common uses for air sensors, how to plan and conduct a study using air sensors, quality assurance and quality control, how to use air sensor evaluations, and finally, data analysis. There are also additional resources at the end of this presentation if you would like more information. The first topic in this presentation focuses on background information on air sensors. This includes general characteristics, common uses and applications, common components, what an air sensor is, and some common types of sensors. In general, when we describe air sensors, we are referring to instruments that are smaller, lower in cost, and easier to move around and use in comparison to regulatory monitoring instruments. Air sensors often return data quickly and more often. For example, data points may be reported every minute. Air sensors can measure some, but not all, air pollutants. And lastly, data quality from sensors is highly variable. For some pollutants, sensors show consistent performance. However, for other pollutants, they don't. Also, sensors are not as accurate as regulatory monitors. Sensor data often needs data cleaning, a process where data is carefully reviewed and false data points are removed. Following data cleaning, sensor data often needs to be corrected. Correction, also called adjustment or calibration, is a process that accounts for the differences between the concentrations reported by the sensor and concentrations reported by the regulatory monitor. All of these steps make sensor data more comparable to data from regulatory monitors. Over the years, air sensors have become more popular and widely used. We have observed a number of trends, including greater interest in knowing about local air quality, greater access to air quality data, and data being visually displayed on maps. Additionally, sensors are being marketed directly to consumers. These trends encourage the increased use of sensors for many different applications, which we'll go over in the next slide. So this slide summarizes some of the common uses and applications for air sensors. Air sensors have been used for short-term emergencies, such as wildfire smoke monitoring, and to understand local air quality conditions. Sensors are also used to explore local source impacts, such as wood smoke, transportation sources, and industrial sources. Additionally, air sensors have been deployed in more locations, so there is finer scale information on air quality. Lastly, sensors are used to promote environmental awareness and education. They are often placed in community areas or schools and used in classroom settings. There are a number of key points to keep in mind for using air sensors. First, sensors are not appropriate for regulatory grade monitoring and should not be used as a replacement for regulatory monitoring instruments. The goals for your air quality monitoring study should help you decide what combination of sensors and regulatory monitors you may need to deploy. Sensors can be useful for what EPA refers to as non-regulatory, supplemental, and informational monitoring, or NSIM applications. Examples of these applications include education and increasing environmental awareness, learning about local or neighborhood air quality, identifying hotspots, supplemental monitoring, and emergency response during wildfires and other events. Another key point is that sensors can produce large volumes of data, and those data may be less accurate. Therefore, you will need to consider how you will store, process, and clean the data before using it. Quality assurance and quality control are critical for collecting good quality data. Lastly, sensor data often needs to be interpreted, especially if an action is desired, such as a change in behavior or to identify pollution sources. It may be helpful to form partnerships with government, academia, or others to assist with data interpretation. For the remaining background information, we will walk through common components and types of air sensors. The diagram on this slide shows the typical components of air sensors. Normally, air flows through the sensors either passively or actively with a pump or fan. Most sensors have a power source, components to detect pollutants or measure other parameters such as weather, communications to transmit data, a microprocessor that controls the device, and an enclosure to house the sensor and protect its components and electronics. Note that this is a simplified graphic and the components may vary from one sensor to another. Air sensors have a number of common names. Some sensors are referred to as Original Equipment Manufacturer or OEM devices. OEM devices are usually raw optical, metal oxide, or electrochemical sensing devices. They have little to no data processing or interfaces on the sensors, and there are a limited number of different OEM types for a given pollutant. Other names include sensor, sensor system, or sensor node. These terms describe a device that has one or more OEM sensors integrated into a device with common data and power management and an enclosure or housing. The system may have active or passive sampling, and the data are generally reported in real time at high time resolution, such as every minute. Finally, these systems are typically designed for different user needs and applications. One common air sensor is a particulate matter or PM sensor. Most PM sensors on the market use an optical detection approach. With this approach, a small range of particle sizes are typically observed, as shown in the figure on the right. This approach converts particle light scattered into an estimated PM mass concentration. The light scattering per particle mass can vary by particle size and composition, as well as moisture. PM sensors offer several benefits. They have good data recovery and minimal downtime, moderate to low intersensor variability, moderate correlation with regulatory measurements, and a reasonable lifespan of about 3 to 5 years. Some considerations to note are that PM sensors tend to be impacted by temperature and humidity, especially high humidity. They can over or under report PM concentrations, and they have a wide variation in precision. This means agreement between sensors of the same make and model could be very good or very poor. Also, PM sensors do not detect very small particles, anything less than 0.5 microns, or reliably measure larger particles with sizes over 2.5 microns. Lastly, while many sensors have identical internal components, the packaging and placement of the components can result in different data quality. Another common type of sensor are gas sensors. The most widespread measurement methods are electrochemical sensors and metal oxide sensors. Electrochemical sensors operate by reacting with a gas and generating an electrical signal that is proportional to the gas concentration. These sensors are sensitive to temperature and relative humidity, need time to warm up, have low power requirements, and have cross-sensitivity to other gases. Metal oxide sensors are made of a semiconductor material which reacts with gases and cause a change in conductivity due to adsorption of a gas. These sensors are sensitive to low relative humidity and have a high power draw because to increase sensitivity and response time, they need to heat up to 200 to 500 degrees Celsius. Subsequently, these sensors also have a slow startup. Additionally, metal oxide sensors have cross-sensitivities to other gases. The chart shows a summary of the availability, accuracy, and reliability of gas sensors for common pollutants. There are several benefits and things to consider with gas sensors. For benefits, There are more commercially available sensors for ozone, nitrogen dioxide, and carbon monoxide. Performance remains highly variable, but the use of multiple sensors and calibration algorithms has improved correlation with regulatory methods, and an increasing number of test results exist. The table on the right is an excerpt from a larger evaluation summary illustrating the performance variability for different gas sensors. As for considerations, sulfur dioxide sensors are not currently effective at low ambient concentrations. Additionally, gas sensors typically lose sensitivity after 6 months to 2 years and therefore need to be replaced more often. This next topic focuses on the differences between air sensors and regulatory monitors. EPA developed a short video that introduces the kinds of outdoor air quality data collected by EPA, states, local air agencies, and tribes, and how those data compare to sensor data. We will now watch this video.
Understanding the kinds of outdoor air quality data that are available and how that data differs can help you determine how they may be used. Let's start with the data collected for regulatory purposes. The Clean Air Act directs EPA to limit levels of air pollution in the outdoor air. The agency sets national ambient air quality standards, called the NAAQS, for pollutants that are common in outdoor air considered harmful to public health and the environment, and that come from numerous and diverse sources. These pollutants include carbon monoxide, ozone, lead, nitrogen oxides, particulate matter, and sulfur dioxide. EPA, states, and tribes place air quality monitors in high population and high pollution areas across the United States to evaluate air quality. These instruments must meet strict EPA or state environmental regulations, both initially and over time. Because our regulatory decisions affect human health and may impose costs to improve air quality, EPA requires rigorous quality assurance and quality control procedures for this monitoring network. These include requirements for where monitors are sited, as well as how samples are collected and analyzed. Regulatory monitors are operated and maintained by trained staff. EPA is confident that the air quality measurements this network provides are accurate. In comparison, air quality sensors can be portable, less expensive, designed to be low maintenance, and require minimal training to operate. So how can we put sensors and their data in context? It depends on your objectives and purpose for measurement. Air quality sensors and crowdsourcing allow for more measurements over space and time. Sensors, for example, may be helpful in hotspot identification, monitor sighting, and exposure pattern identification. They can also help inspire behavioral changes and educate people about pollution where they live, work, and play. However, sensor performance can be highly variable. They may provide less accurate measurements than regulatory monitors and may not operate well in extreme environments, like high temperatures, humidity, or pollution. Also, many people operate sensors with limited, if any, quality assurance. Currently, some sensors lose their ability to take accurate measurements over time. Finally, sensors may provide data outputs every minute or second. Note, with more frequent sampling, there can be greater uncertainty in the measurement itself and how to interpret any potential effect on your health. If you're looking at sensor data, you need to ask yourself some questions about what you're seeing and how to make sense of that data. Where can I go to learn about the performance of different sensor units or manufacturers? How will I use the information to inform decisions about outdoor activities? How should I interpret the raw or processed sensor measurements? Are the measurements collected every second, minute, 15 minutes, or hourly? How does this information compare to what EPA shows on air now? These questions are important to consider when deciding how and when to use regulatory versus sensor data. Learn more at epa.gov/air-sensor-toolbox.
A frequent question is, how do air sensors compare to regulatory monitors? This table summarizes some of the main differences. Regulatory monitors typically cost between $15,000 to $40,000 US, whereas air sensors cost $100 to $5,000 US. Using a regulatory monitor requires highly trained technical staff. Little to no training is needed to use an air sensor. It is expensive to operate a regulatory monitor, and it must be in a fixed location with power and temperature control. Air sensors are less expensive to operate and are more portable as long as they have basic weather protection. The data quality from regulatory monitors is reliable and consistent in different conditions, whereas the data quality from sensors is more variable, and different weather conditions and pollution levels can impact data quality. Regulatory monitors typically last for 10 years or longer with calibration and maintenance to remain accurate. Air sensors have a shorter lifetime, estimated to be about a year, or in some cases it is unknown, and they may become less accurate as time goes on. Finally, regulatory monitors are the only type of monitor that can be used for regulatory monitoring purposes. The next topic focuses on common uses and applications for air sensors. There are a number of uses for air sensors. As mentioned earlier, air sensors are often used for non-regulatory, supplemental, and informational monitoring applications. As shown in the table, we have broken these applications into 3 categories and provided examples for each. The first category is spatial temporal variability, which involves characterizing a pollutant concentration over a geographic area and/or time. The next category compares differences or similarities in air pollution data against a threshold value or between networks for different locations, regions, times, etc. The last category is long-term trends, where changes in pollutant concentrations are analyzed over a period of time, usually years. The next few slides will go over 4 example applications. An example of the spatial temporal variability application category is the use of sensors in education. This application helps people learn about air quality and increases awareness about air quality and sensors by looking at changes in pollutant concentrations within a given area or over time. Teaching topics can vary from environmental awareness, air quality, sensor technologies, electronics, graphing, and programming and coding. Many organizations have developed resources that can be used for the classroom, individual instruction, community workshops, and other educational settings. Examples include lesson plans, data analysis tools, how-to guides for building sensors, and guidebooks on using sensors. Additional resources are included here for more information. The remaining examples relate to the comparison application category. In this example, sensors are used for hotspot detection. A hotspot is an area where pollutant concentrations are higher than the surrounding area. Typically, the goal of hotspot detection is to understand the differences in air pollution levels within a certain area or at potentially impacted sites, or to identify possible sources of emissions. Hotspot detection is usually conducted using mobile measurements or a fixed site network. For mobile measurements, sensors are mounted on a car, bike, or person, and measurements are collected to map pollutant concentrations and find hotspots in a community. The figure on the right shows an example of mobile measurements collected by sensors on a vehicle. In a fixed site network, measurements can identify areas with elevated pollutant concentrations. Hotspots are often caused by emission sources, so measurements are typically collected closer to the source or suspected source of emissions. The second example of a comparison application is supplemental monitoring. This type of monitoring fills in gaps in areas where there are limited or no regulatory monitors and to identify sources of interest or locations that may need further study and monitoring. To achieve this, sensors are placed in locations that do not have existing regulatory monitors. The data collected are not meant for regulatory monitoring purposes, but may help complement existing regulatory monitors. Since sensor data is not as accurate as regulatory monitor data, it needs to be cleaned and corrected to make it more comparable to regulatory data. The final example of a comparison application is emergency response. The goal of emergency response is to quickly gather information on air quality conditions, communicate those conditions promptly to protect public health, and continually monitor air quality to make sure levels are safe. Sensors are placed in areas that are, or potentially could be, impacted by air pollution emergency events like wildfires or volcanoes. Often during these types of emergency events, air quality can worsen rapidly and impact human health. Sensors that respond quickly to concentration changes but may have less accuracy are normally adequate for emergency events and signaling any actions that need to be taken. In this next topic, we will talk about planning and conducting a study using air sensors. We will discuss the steps needed to plan and conduct a study, which includes information on how to determine your purpose or goal, develop a plan for monitoring, including selecting a sensor, select monitoring locations and install sensors, check the performance of a sensor via co-location, collect and manage the data, and analyze, interpret, and visualize the data you've collected. Careful planning is critical to ensuring a project's success. There are 5 key steps involved in planning and conducting an effective air monitoring study. Following the wheels shown, those steps include 1. Determining the question you are trying to answer. 2. Developing a plan to obtain the data needed to answer that question. 3. Setting up the sites and sensors in preparation for measurements, including pre-study co-location and testing. 4. Collecting measurements and reviewing the data. And 5. Analyzing and interpreting the data so that results can be communicated and actions can be taken. The wheel also reminds you to consider actions to ensure high-quality data during all project phases, and to periodically consider whether the question has been answered or if the plan needs to be revised. You will notice that sensor selection is one of the last tasks listed in the plan section. It is important to consider what measurements and data quality are needed before selecting a suitable sensor or group of measurement technologies. In the next few slides, we will further discuss each of these key steps. Step 1 is question. Determine your purpose for monitoring, or the question or questions you want to answer. The best questions seek to understand and address a concern or suspicion and can be answered using available resources. When coming up with a research question, it is best to be as specific and detailed as possible. The example shown here illustrates how a question can be improved by making it more specific. These additional details help you tailor a monitoring plan to obtain the answers you are seeking. Some questions can be answered without collecting additional data. You can determine if there is a need to collect more data by asking the following questions. What do I already know about the concern? What is unknown that I want to understand? What may have caused the concern? What are my desired outcomes? Are there nearby regulatory monitors, and what pollutants do they measure? And finally, what available resources do I have? This includes people, time, skills, and funding. It's important to remember that air sensors can measure some, but not all, air pollutants. So, air sensors, or air sensors alone, may not be able to answer all of your questions. Additionally, it is important to remember to define the need and purpose for monitoring before beginning data collection. Step 2 is plan. Developing a plan ensures that useful data are collected for the application of interest and helps identify potential problems early on. The plan should include 1. the purpose and goal for monitoring. 2, the roles and responsibilities of project participants and collaborators. 3, the pollutants, environmental parameters, or other data that will be collected or used. 4, backup plans if something changes during the project. 5, documentation or records on how air monitoring will be conducted, such as standard operating procedures for operating the equipment, quality assurance and quality control procedures, site logbooks for field observations, etc. 6, details about what instruments will be used to collect the data. 7, details about how the data will be collected and transmitted to a storage location. 8, procedures for maintenance, operation, and troubleshooting of the instruments. 9, details about where data will be stored, how it will be processed, who will have access, and how data will be accessed and managed. And finally, 10, information about data analysis methods and visualization. As you can tell, there are many details to consider when developing a plan. It will be useful to document the details in writing and to agree on the plan with all collaborators. At the bottom of this slide, we have provided a link for more information on documenting a study plan and a quality assurance project plan. Now that you have a plan, you are ready to begin the sensor selection process, but there is still a lot to consider. The first step is to ask questions to help match sensors to your application. Some questions to consider are shown in the infographic on the right, which can also be accessed through the link to the Air Sensor Toolbox provided below. Let's walk through these questions. Question 1. What are my goals? The data quality you need from a sensor may vary depending on your goals. For instance, you might need a more accurate sensor to understand personal exposure, but could use one that is slightly less accurate for environmental education. Question 2. What measurements are needed to meet my goals? You may decide you need multiple measurements to answer your question. For example, you may want to measure pollutant concentration and wind direction to determine if a source is impacting your community. You may find one sensor that measures everything you need, or you may have to consider a combination of different technologies. Question 3. What design features do I need? Based on where and how you want to make measurements, you can identify the features that are most important to you. For instance, if you want to walk around to make measurements, you will need a battery-operated device. Question 4. What are some factors that can influence the cost of buying and operating a sensor? The purchase price of a sensor is just one thing to consider. Owning and operating a sensor can have additional costs, especially when you consider data analysis and visualization. We have suggested some other costs that may apply so that you can ask informed questions and factor these costs into your purchasing decisions. Question 5. How do you know if the air sensor is accurate? Sensor performance varies, and consumers can benefit from looking at evaluation reports to better understand how a sensor might be expected to perform before making a purchasing decision. You might consider whether the evaluation was done in a location similar to where you plan to use the sensors, and consider how data was processed in order to produce the results shown in the evaluation. And finally, question 6. What details should I look for in a user manual? Today, the amount of information and documentation available from a manufacturer is variable. Some materials will come in printed forms, while others are only available electronically. We have suggested some topics that you can look for in the available documentation. If you do not find the information you need, you may want to ask the manufacturer before making a final purchasing decision. When selecting a sensor, it is also important to consider a few other criteria, such as the measurement range and detection limit of a device. Sensor performance may vary if pollutant concentrations are high or low. Some sensors may have trouble detecting pollutant concentrations when they are very low. Sensor accuracy, or how comparable the sensor measurements are to nearby regulatory measurements, may be important if your project requires you to compare these measurements. Today, most air sensors still require calibration or field co-location and data cleaning and correction in order to produce data that are more comparable to regulatory measurements. These procedures can vary in complexity and effort, and you will want to understand the requirements and effort upfront. If your sensor will be moving, or if measurements will need to be correlated to changes in wind speed or direction, you may need to consider the response time of the sensor. Lastly, you will want to consider general features such as durability and power needs. Now that you know what you are looking for in a sensor, the next step is to research what is available. Sensor evaluation reports may help you identify or narrow down your options based on performance. So where can you find sensor evaluations? The AQ-Spec website is a great place to start. They have detailed field and laboratory testing reports, as well as shorter summaries that provide evaluations for various sensors compared to the reference or regulatory monitors. In addition, they host pages about each of the sensors they have tested with links to information describing the sensor's features. The US EPA and the European Commission Joint Research Center have also conducted sensor performance evaluations. Users may also find value in the Air Lab Microsensor Challenge results. Prospective users can always ask a manufacturer for evaluation reports. As evaluation efforts expand, other resources may become available in the future. The Learn More link at the bottom of this slide will take you to another part of this presentation where we will discuss the interpretation of sensor evaluation reports in more detail. The third step in planning a study is setup. Once you have selected sensors and know what will be required in terms of power, communication, mounting, and maintenance, you are ready to decide where to site them. Depending on your project goals, you may be looking for sites for one sensor or a network of sensors. You will want to find an appropriate co-location site too. Using the infographic on the right, we will step through some of the logistical considerations. First, general location. Consider the purpose of your measurements when deciding where sites should be located. Next is access. Determine the requirements to visit the site to install and service the sensor. This could include permissions needed to enter the site, keys, etc. Next is power. Running power can take a significant amount of time and money, so determine requirements and establish power early. Next is communications. Ensure communications are reliable, such as cellular or Wi-Fi service, before installation. Next is security. Ensure that the sensor is secure and protected from vandalism or theft, and that site operators can remain safe. Next is placement. In general, place the sensor at least 6 feet above ground level, the rooftop, or other objects, and away from obstructions, vegetation, or emission sources that would interfere with the measurement. When you are ready to start installing, there are 2 more recommendations. First, photos. Take photos of the sensor installation and the area surrounding the site. And second, documentation. Record details about the site and installation. These items may come in handy when describing the project and interpreting the data later. Once you have decided where sensors should be located, you can visit the link to the Air Sensor Toolbox webpage at the bottom of this slide for further guidance. Now, let's talk more about co-location. Co-location is the process by which sensors are placed near regulatory instruments and operated at the same time and place under real-world conditions. This allows for comparison of the sensor data to the reference or regulatory data so that you can evaluate how a sensor performs. Collocation helps to quantify important parameters such as accuracy, precision, and bias, which are terms we will define more in detail later. Finally, if needed, the data gathered can help you develop correction equations to improve the sensor data accuracy. It is important to note that collocation is most valuable if the sensors are evaluated under conditions which are similar to where you plan to use them. In other words, sensors should be co-located in a place that has similar pollutant sources, pollutant concentrations, and meteorological conditions. There are many different approaches to co-location, and each has its own considerations. Some general tips for co-location are to locate the sensor as close to the regulatory grade or reference instrument as possible. Co-locate for an adequate number of days, and be sure to measure meteorological conditions, as these can impact sensor performance. What do we mean by an adequate number of days? This phrase is intentionally vague because it depends on the scope and purpose of your project. Our recommendation is to capture enough data so that the sensors experience the conditions that you expect to encounter once you move them elsewhere. That means the same range of pollutant concentrations, temperature, and humidity. If you are using the periodic all-sensor co-location strategy, this may mean you'll have to repeat a co-location when the season changes or after several months to check for gradual changes. For longer-term projects, you may need to consider one of the other co-location strategies in the table on the right. For short-term exploration studies, we've listed some minimum co-location suggestions at the bottom of this slide. EPA has created two key resources to help you with your co-location efforts. The Co-location Guide gives step-by-step instructions for conducting a co-location and interpreting the data. The Excel-based macro analysis tool will help you time align, average, and plot your co-location data for easier analysis. You can find both resources using the links provided here. The fourth step in planning a study is collect. Collecting high-quality measurements includes many additional tasks beyond setting up the sensors to start recording data. Frequent data review helps detect problems early on, minimizes data loss, and determines when to conduct maintenance. Sensor maintenance, such as cleaning internal components and replacing filters, ensures that sensors are operating properly. Troubleshooting and resolving problems with the sensor ensures reliable data collection. Quality control checks, which can include reviewing data for problems such as outliers or loss of response, help to identify data issues that can be corrected early on. Lastly, periodic co-location helps monitor for changes in sensor data accuracy over time. Managing the large volume of data from a network of sensors is no easy task. It's important to plan how you will manage the data before deploying the sensors. The amount of data can be overwhelming to store, manage, process, and visualize. A data management system can help to ingest, store, and process data, control system settings, and distribute data. Some existing data management systems utilize open source software free of cost, while others have cost structures that depend on data volume or access. We recommend data management system features such as tools for data quality control, review and visualization, automated alerts and emails for missing data, regular data backup, the ability to track changes in firmware, metadata, and/or data manipulations, U.S. Air Quality Index calculations and formulas, data security, and data ownership terms and usage rights. The fifth step in planning a study is to evaluate. Analyzing air sensor data includes several steps, consisting of cleaning data, documenting changes or adjustments, obtaining data from other sources to aid in analysis, averaging and grouping data, and correlating and comparing data to other sources of metrics, like the U.S. Air Quality Index. There are many visualization options that may help you interpret your data. These include time series plots, scatter plots, calendar plots, maps, and wind roses. The best approach for your study will depend on the research questions you want to answer. Many software tools are available to assist you with data analysis and visualization. These next two slides go over some of the options and their features. The Real-Time Geospatial Data Viewer, or ReadyGo, is a free web-based tool for exploring environmental data collected using stationary or mobile platforms. Spreadsheet software such as Microsoft Excel or Google Sheets allow for simple data processing and visualization. Geographic Information Systems, GIS, applications such as Google Earth and ArcGIS Online provide frameworks to gather, manage, analyze, and store spatial data. Some local air quality agencies have developed tools that are available online. Commercial cloud-based software packages such as Power BI, Click, and Tableau allow users to upload data and perform data analysis and visualization. These packages do have a cost, but some may offer free trials or lower cost for students and nonprofit organizations. Some sensor manufacturers have developed analysis and visualization tools too, but these tools may be limited to their sensor devices. R is a free open source software for statistical computing and graphics. It can handle large data sets and has a large user community with many online resources. Some air quality specific add-on packages are also available. Finally, Python is a free, open source programming language that can handle large data sets and can be used for data processing, data visualization, statistical analysis, and graphics. Now that we've walked through the overall process of planning and conducting an air monitoring study, let's spend a little more time talking about quality assurance and quality control, since these steps are vital for collecting good quality data. Quality assurance and quality control, referred to as QA/QC, ensures that credible and useful data are collected. QA/QC should be incorporated into each step of your project. So, what's the difference between quality assurance and quality control? Quality assurance is essentially the planned steps you'll perform to manage the project and collect, assess, and review the data so that it will meet your data quality expectations. Quality control refers to the actions, steps, or technical activities you'll take to limit error in the measurements you collect. The definitions of QA/QC may seem a little abstract, so let's consider some concrete examples that apply to air sensor data. A quality assurance plan can include developing a plan for air monitoring and routinely checking and reviewing data. Quality control actions can include frequent data review, checking units of measure, timestamps, and data completeness, regular maintenance of sensors, periodically cleaning sensors, and performing calibration, collocation, and data correction procedures. To assist you with your quality assurance plan, EPA has created the Citizen Science Handbook. This resource provides information on how to ensure that you collect good quality data. The handbook includes templates to assist in developing a quality assurance project plan, or QAP. A QAP is encouraged for all projects and may even be required depending on your funding source or the end use of your data. It documents how an organization has used quality assurance and control to ensure the data collected can be used for the intended study purpose. So why should you care about quality assurance and quality control? Well, there are 5 key reasons. It helps to ensure a successful project, gives you more confidence in your results, ensures data collected can be used for the intended purpose, helps others understand the quality of the data being produced, and provides transparency in your data collection methods. To be able to draw conclusions from your data, you need to carefully document your activities and procedures. Your quality assurance plan should document answers to 6 key questions. What is the purpose of the project and the question you want to answer? How and where are you planning to collect samples, data, or other information? How are you training the volunteers to collect samples, data, or other information? How will you control for errors in the field, in the laboratory, or during data analysis? How will you check your data and determine if it is useful? And lastly, where do the data go and who will look at the data? This topic will focus on how you can use online air sensor evaluations to decide which sensor to use and to understand how your selected sensor compares to regulatory monitors. Given that there are many air sensors on the market, it can be difficult to know which ones perform well and how they compare to regulatory monitors. Air sensors are evaluated to understand how they perform under ambient or field and controlled or laboratory conditions. Results are often shared with the public and can be used to help you understand how a sensor performs and decide which air sensor would best suit your needs. Air sensor performance evaluations typically provide detailed information about field and lab test results of air sensors. Evaluations include information about the sensor model and version, regulatory and other instruments used for comparison, concentration range of pollutants during a test, precision, bias, linearity, error, data completeness, graphical plots, and summary tables. As a reminder, you can find sensor evaluation results in many places, as listed on this slide. This is an example of air sensor evaluation results from research conducted by EPA. In this report, the top section contains detailed information about the field deployment, such as who conducted the testing, test location, sampling timeframe, and sensor and regulatory monitor information. Information about the sensor, make, model, and firmware version is also included. This can be particularly useful in helping users determine if a sensor is currently being sold or if any improvements have been made to the sensor. This next section of the evaluation report provides time series plots, which show how measurements change over time and help determine if the sensors capture the same variation in measurements as the regulatory monitor. In the plot, the red, blue, and purple lines represent the air sensors. As you can see, pollutant concentrations are well captured by the sensors, and the sensors show very similar measurements to each other. However, the sensors tend to over-report measurements relative to the black line, which represents the regulatory monitor. Next to the time series plots are scatter plots showing how sensor and regulatory monitor measurements compare. These plots can also help you understand if a sensor over-reports or under-reports data. In our example, the data points are colored red or blue hues based on the relative humidity level. This information is important as some sensors can be impacted by humidity. The next slides will go over scatter plots in more detail. Scatter plots are commonly used to compare air sensor and regulatory monitor data. We will use the figure on the right side of the slide to further explain how to read these plots. The black line going through the dataset is the slope-intercept line, which is created by a linear regression function. The slope-intercept line is represented by the equation y equals mx plus b, where y is the sensor measurement, x is the regulatory monitor measurement, m is the slope, and b is the y-intercept. R squared is the coefficient of determination, representing a measure of how close the data points are to the slope-intercept line. R squared ranges from 0 to 1, where values closer to 1 indicate a stronger correlation and less scatter. The 1-to-1 line, shown in the figure as a dashed line, represents perfect agreement between sensor and regulatory monitor data, or where y equals x. If the slope-intercept line is the same as the 1-to-1 line, there is a perfect agreement between the two measurements. The slope-intercept line can help you understand if a sensor overreports, also called overestimates, or underreports, also called underestimates, concentrations relative to regulatory monitors. The plot on the left shows an example of a sensor that overreports, where the sensor measurements are higher than the regulatory monitor measurements. The plot on the right is an example of a sensor that underreports, where the sensor measurements are lower than the regulatory monitor measurements. Returning to the air sensor evaluation report, the next section provides information on performance metrics. These metrics are recommended as part of EPA's protocols on evaluating performance of PM2.5 sensors. The dots in the light gray space indicate that the sensor does not meet the target, and the dots in the dark gray space indicate that the sensor meets the target. The chart below shows the recommended performance metrics and target values for PM2.5 sensors, and more information can be found on the webpage provided. The bottom section of the evaluation report provides plots of meteorological data which show conditions during deployment and help visualize the impacts of temperature and relative humidity on sensor measurement. The figures on the left show that the temperature and relative humidity levels are normally distributed over a wide range. The conditions shown can be used to compare conditions to your planned location and study season. The figures on the right show the sensor measurements correlated with temperature and relative humidity, with temperature decreasing and relative humidity increasing. This suggests that a correction equation may need to include meteorological data to make the sensor data more accurate. There are some key takeaways on air sensor performance evaluations. First, performance evaluations can provide useful information on how a sensor performs in either a field or lab environment. It's helpful to keep in mind that testing protocols, performance metrics, and how a metric is calculated can vary, so this information should be carefully reviewed. Next, R squared is a common metric used to understand sensor performance. However, it is just one indicator of performance. It is important to look at the detailed summary report to best understand sensor performance. Additionally, it is important to remember that while a sensor may perform well in certain conditions, it may perform differently if the device is operated in other conditions. Remember to always carefully review the test conditions. Lastly, there are many useful resources available on sensor testing protocols and sensor evaluation results, some of which are listed on this slide. The next topic will focus on data analysis and interpretation. As mentioned previously, it's important to review your data as it's being collected so you can identify any problems as they arise. But what should you look for? It's impossible to detail every possible issue you may encounter, but we'll outline some of the common data review steps to help you get started. We suggest looking at the measurement range. Are the concentrations, peak to valley, within the range you would expect for this location? Are there any concentrations that are abnormally high or low? These could be outliers. Are there any sudden changes in the data that last only a moment and can't be correlated to something happening nearby? We might call these spikes. We expect many pollutants to exhibit a pattern in the rise and fall of concentrations throughout the day. You can look for those patterns. Gradual or sudden changes in a sensor's response over time may be observed. These are referred to as drift or shifts. Flagging data is a way to tag any abnormalities within the data set. Regulatory monitoring requires that data qualifiers or notes about the data be added to data sets to explain missing data, null data, and invalid data. Common qualifiers include quality assurance flags, such as this concentration exceeds the instrument's upper range. Null data flags, such as data is missing due to machine malfunction, power failure, or because it was voided by the operator. Informational flags, such as notations about fireworks, high winds, or traffic disruption. During data analysis, you may have reason to exclude data with a subset of these flags. Sensor data is often collected at high time resolution or at a frequency of every 5 minutes, 1 minute, or faster. Averaging data up to 1 hour, 8-hour, or 24-hour averages can help improve the quality, usefulness, and manageability of your data. Data are often averaged to facilitate comparison to measurements from another instrument or environmental standard. Comparison to a health-based benchmark, like the U.S. Air Quality Index, will require data averaging in comparison to a nowcast AQI and would require additional calculation using the nowcast formula. Averaging times will vary by application. For example, 1 hour or 24-hour averages are useful to examine pollutant concentration trends. To connect spikes in the data with the sources that may be causing them, either no data averaging or a shorter averaging period may be needed. Sensor data can be noisy and highly variable. Sometimes this variation is real, such as when someone smoking walks by the sensor. Other times, the variation can be caused by electronic signal noise. Averaging data can help reduce the influence of random error, smooth out short-term events, reduce noise, and better represent trends in the data. For example, the graph on the bottom shows ozone data at 1-minute intervals in red and at 15-minute averages in green. You can see the red line has many peaks and dips, but when averaged to 15 minutes in the green line, the variation is smoothed out, making it easier to see the general trend throughout the day. As mentioned earlier, sensor data needs to be averaged before being compared to the U.S. Air Quality Index. The U.S. AQI is one way of communicating air quality. The index allows users to quickly connect the air quality with a level of concern, the associated health effects one might experience, and actions one can take to protect their health. In general, when the US AQI is green, the air quality is satisfactory and air pollution poses little or no risk to your health. As you move down the chart into other color categories, there is more concern and elevated risk, particularly for sensitive groups such as people with heart or lung disease, children, and older adults. Official US AQI values are calculated using the averaging times listed in the U.S. National Ambient Air Quality Standards, or NAAQS. The PM2.5 AQI is based on a 24-hour average, while ozone is based on an 8-hour average. Once the data have been collected, reviewed, cleaned to remove outliers, spikes, and any flagged data, and then averaged, you can move on to exploring the data through visualization. Many types of plots and visuals can be used to look at your data. The type of plot you choose should be based on the questions you are trying to answer. Let's discuss two common types of plots: time series plots and scatter plots. Time series plots are a useful way to visualize sensor data and are commonly used to show how measurements change over time. This is also known as temporal variability. Time series plots can help to answer questions such as, when do high and low measurements occur when comparing different sites? Are measurements higher during certain times? For example, does PM 2.5 increase next to the road during rush hour? Are there patterns to measurement changes? For example, are PM 2.5 measurements higher during morning rush hour? Scatter plots are commonly used to show the relationship between two variables. Scatter plots can help to answer questions such as, is there a relationship between two parameters of interest? How does an air sensor compare to a regulatory monitor? Does an air sensor over-report or under-report measurements? This topic will help connect you with a variety of additional resources that can provide additional knowledge beyond what was shared in this introductory training. The US EPA's primary portal for sharing information and resources is the Air Sensor Toolbox webpage. Select resources are also available in Spanish, and a link can be found on the main Toolbox webpage or through EPA's Spanish language portal. Several guidebooks and recommendations are available to help you get started. US EPA's Air Sensor Guidebook provides information on air quality basics, purchasing and using air sensors, planning, conducting a study, understanding sensor performance, and much more. Through an EPA STAR grant, the South Coast Air Quality Management District released Community in Action, a comprehensive educational toolkit on air quality sensors, in September of 2021. Their guidebook provides information on project planning, operating sensors, and understanding the data. The toolkit provides other helpful resources too, including several training videos. The report, Recommendations for the Development and Implementation of Distributed Sensor Networks, is a blueprint which summarizes lessons learned, best practices, and research questions for developing and implementing sensor networks. Finally, in late 2020, the World Meteorological Organization released their Update on Low-Cost Sensors for the Measurement of Atmospheric Composition report, which provides an update on the use and operation of sensors to measure atmospheric composition. The US EPA provides information for the public about how it collects and uses air quality data, communicates air quality health risks, and interprets data collected using air sensors through the use of short informational videos. This video series is available in both English and Spanish and can be found from a link on the Air Sensor Toolbox webpage. Further guidance is available to help you site and install air sensors. The US EPA has created a webpage with recommendations on how to site air sensors for both outdoor and indoor installations, and provides recommendations on how to document the installation with supporting information. As part of their sensor toolkit, the South Coast Air Quality Management District has provided a written sensor installation guide in both English and Spanish, both of which are available on their website. The US EPA also provides several educational resources that support sensor use. The Educational Resources page links to 5 fully developed hands-on lesson plans for classroom, group, or individual instruction, focusing on outdoor air, indoor air, personal exposure, the role of vegetative barriers, and fire and smoke. All lesson plans include instructor and participant guides, introductory slides, worksheets, a resource guide, frequently asked questions, and align with next-generation science standards. The page also has links to other activities and lesson plans, including a build-your-own particle sensor kit, lesson plans which use the Air Mapper and ReadyGo, and lesson plans focused on vegetative barriers. We hope that you find these resources informative and that you discover several more as you explore the select few that we've highlighted here. During this presentation, we've mentioned a number of terms that may be new to you. For quick reference and easy access, we've listed several with their definitions on this slide. We thank you very much for your time and attention and welcome you to reach out to the slide authors with any questions you may have.